All right, atomic anomaly confirmed. Evidence of a dark force. What?
Welcome back for another episode of Anomaly Watch. Today I have an update on a peculiar anomaly in the behavior of an atom that could be evidence for a dark force, as the headlines put it. A new experiment looked for the anomaly and confirmed it. This anomaly is young. It was first detected in 2020 by a group at MIT. They studied atoms of ytterbium, which is a metal with atomic number 70. The anomaly was originally at roughly 3 sigma, but it's now jumped to a stunning 23 sigma. Ytterbium is not a very common element unless you work in nuclear physics where it's super popular. This is because ytterbium has a special property. Like most elements, it has several isotopes. That means its atomic nucleus can have different numbers of neutrons. Now, if you add neutrons to the nucleus, that makes the nucleus bigger, but keeps the electric charge the same. This very slightly changes the electron energy levels in a way that depends on the properties of the nucleus. And ytterbium just so happens to have the perfect number of neutrons and protons in the nucleus to make its electron energy levels very sensitive to changes in the neutron count. This means that if you compare different isotopes of ytterbium with each other, you learn a lot about the nuclear structure. This is why physicists like to hit different isotopes of ytterbium with laser light at different frequencies and then check what comes back. The laser probe tells them where the electron energy levels are, which in return tells them something about the interaction between the nucleus and the electrons. Then they compare the responses of different isotopes, which is called the isotope shift. This isotope shift should have a predictable dependence on the frequency, but here's the rub, the data don't comply. The 3 sigma deviation, which the MIT guys found in 2020, isn't much. It could happen with a chance of 1 in a few hundred, just coincidentally. It's not the thing that keeps you up at night, unless ytterbium is your best friend. So, of course, nuclear physicists looked into this closer. The authors of the new paper poked ytterbium again, but this time they used a super precise measurement technique called a frequency comb that's great for teasing out
Comb.
fine details of a light spectrum. Frequency combs even got a Nobel
Comb.
Prize in 2005. And here's the banger. Using this technique vastly increased the mismatch between data and predictions. You can see this here in this figure, where the red line is the prediction and those are the data points. The error bars are increased by a factor of 200 because otherwise you wouldn't see them. There could be multiple reasons for this, but either way you look at it, they say, there needs to be some extra contribution in addition to the nuclear physics that they did already use, which is in nuclear deformation. They write in the paper that they deduce a 23 sigma preference for more than just the nuclear deformation going on, and that this leaves open the possibility of a new boson being responsible. So they don't say that this must be a new particle, but that a new particle would explain the mismatch. They calculate that the new particle would have to be one of medium mass, with a mass somewhere in the range of a few mega electron volt. You may wonder now, well, but why then have we only seen it in ytterbium and not elsewhere? The reason is not to do with the boson, but with ytterbium. This particular chemical element just so happens to be extremely sensitive to any sort of interactions at nuclear scales. It's quite plausible that if such a boson exists, you'd see it first in such an experiment. If this deviation is due to a new boson, and that's a big if, this would be huge. It'd mean there is an additional interaction not accounted for by the standard model. It could solve a lot of problems, such as dark matter or the unification of forces. This is why it's sometimes called a dark force, because it's what we'd expect from a force that stems from dark matter particles. However, nuclear physics is much more difficult than particle collisions, because atomic nuclei are made up of so many individual particles. It could be that this strange signal just comes from some badly understood behavior of the atomic nucleus. Also new physics in some sense, but not such a groundbreaking revelation. Still, I think it's worth keeping an eye on. The element ytterbium, by the way, is named after the Swedish village Ytterby, where it was first discovered.
Really?
Ytter means outer and by means village. So the proper translation would be outer villagium, which sounds like a self-help retreat for a brain cleanse.
Thank you.
Though personally, I suggest that if you need a brain cleanse, you stare at a text form. Works for me every time. Did you know there's a free...
Wow, thanks, Sabine. That was actually pretty cool. That was pretty cool. I mean, that's just a little extra anomaly here. You know, there's all these anomalies add up and give you something to think about. But that was really well explained. I'm just, wow, that's pretty cool. So essentially, what you have is a result that can only be explained possibly by X-ray interactions within the nucleus that we currently do not have in our models, or if we keep our model, then possibly this dark boson. Yeah, I mean, that could be interesting. What if these dark bosons are dark matter, but then... Yeah, it's interesting.